Hey, my name is Stefan Nagy. I'm a PhD student at Virginia Tech, and I'm here to present our paper, Full Speed Fuzzing. This is a joint collaboration between my advisor, Dr. Matthew Hicks, and myself. So hopefully today will help get you excited about our efforts to improve fuzzing performance. Uh-oh.
Can we advance the slide?
All right. So as we've discussed already in this session, fuzzing is a very fundamental and time-tested technique to finding software bugs and vulnerabilities. It's very widely used by developers and attackers alike. It spawned many numerous tools like AFL, HongFuzz, and LibFuzzer, each of these with very impressive track records of disclosing vulnerabilities. It's very popular in the software industry. So big corporations like to use fuzzing to find bugs and vulnerabilities in their software, both pre and post-release. And it's becoming very accessible to developers in the form of cloud platforms. And by far the most popular approach in fuzzing is called coverage-guided fuzzing, which at a high level operates given as follows. So given a target application and some test cases for it, the fuzzer executes these these test cases against the target application and measures each one of their code coverage, basically how far they get in the target application's code. And test cases which increase code coverage are preserved, meaning they've found some new part of the code that the other ones have not. And all those which don't are simply discarded along with their code coverage. And the end goal of this process is to kind of exhaustively traverse the program code and find those few test cases that trigger bugs or vulnerabilities. Now, to date, a lot of work has gone into improving this test case generation process to mutate test cases better so that they penetrate deeper regions of the code. But our focus is on improving this test case generation process. And we observed that identifying coverage increasing test cases requires the tracing of code coverage for every single test case, yet only a very small handful of these actually increase code coverage. The overwhelming majority, along with their code coverage, are simply just junked and discarded by the fuzzer. And additionally, given this fact, as well as our results show that this process of tracing every test case adds some pretty non-negligible overhead over the course of fuzzing an application, we see this as having a huge potential for improvement, and that these resources could be much better used elsewhere to find bugs in the fuzzing workflow. And this is where coverage-guided tracing fits in. So rather than tracing every one of those single test cases to find the few that are coverage increasing, we restrict tracing to just those that are coverage increasing, that small fraction. And as a result, we were able to dramatically cut down this overall overhead to about 0.3%. And because we focus on simply filtering out test cases before they are traced, we would easily complement these great approaches which try to generate test cases better or make tracing faster by other means. So our first question going into this project was, how are coverage increasing test cases found? And the answer is fuzzers trace the coverage of every single test case. And they do this through instrumentation inserted either dynamically or statically. And generally, any kind of dynamic instrumentation is far, far slower than any kind of static instrumentation approach. But another limiting factor is the availability of the program source code. So you're able to instrument these kind of white box techniques, which we see as encompassing kind of compile and assembly time instrumentation. That's generally much, much faster than any kind of binary only or black box approaches we refer to in the paper. So going on from that, we wanted to identify how do fuzzers actually spend their time while they're trying to find bugs in an application. So we profiled AFL, which is kind of the standard naive-based fuzzing approach, as well as Driller, which is an advancement that complements these kind of naive fuzzing techniques with a more technical symbolic execution approach. And we looked at black box QEMU-based tracing for both AFL and Driller, because that's all that Driller supported at the time, as well as Klang's out-of-the-box assembly time white box tracing approach. And we profiled these 1-hour executions for 8 benchmarks per configuration. And we discovered that across every one of these configurations, over 90% of fuzzer time was spent on tracing and executing these test cases. So from there, we were thinking, okay, that's a pretty overwhelming majority of time. That must mean that a lot of these test cases are actually coverage increasing. And to our surprise, that's quite far from the truth. So on average, less than 3 out of 10,000 of these test cases actually increase code coverage. So the other 9,000 997 were completely just discarded. So going on from there, we were thinking, okay, 1 hour is kind of short. Let's try 24 hours. That's kind of the standard evaluation trial for fuzzers. So we looked again at AFL QEMU. We collected 5 24-hour test case dumps per 8 benchmarks. And we discovered that actually it decreases exponentially. So as you kind of push past and fuzz your easy to reach regions of the target application's code, it becomes exponentially less likely that you will find test cases which reach new code coverage. So on average, this ended up being at most 1 out of 10,000 test cases on average. So very, very low. So from here, the overall impact is, okay, we're spending over 90% of fuzzer time on tracing these test cases, yet over 99.99% of these are completely just discarded by the fuzzer. So this is analogous in our eyes to trying to find the needle in the haystack by taking a magnifying glass to every single piece of hay. It's just not efficient whatsoever. But why is tracing code coverage so expensive in the long run? Well, the answer is you're storing coverage for many, many parts of the program code. So this kind of operates, given you're executing the program, you hook every single basic block and you store that it has been covered in this kind of data structure. AFL uses bitmaps. Arrays are also a common way of doing this. And then you return control flow back to the basic block, finish executing the rest of it, and then move on to the next basic block. But the problem is this process of fetching and writing to this data structure adds many, many instructions to the overhead of this basic block. And because you have many basic blocks in modern applications and execution paths are long and contain all this kind of looping behavior, this overhead very quickly adds up over time. So it is costly to do this excessively. And this is where coverage-guided tracing tries to fit in and solve this problem. So our guiding intuition is that rather than tracing test cases to find coverage that way, we want to find the few coverage increasing test cases without having to trace every single one of these test cases generated. So rather than using a magnifying glass on every single piece of hay, we're just going to stick our hand in there, get poked, and then realize we found the few coverage increasing test cases that way. So it's a lot more efficient. So how this looks like on a micro scale, so we, instead of relying on tracing instrumentation, we use interrupts. So in this application here, let's say we want to track the coverage of block B1, this kind of starting point of the control flow graph, and we would write the first hex byte of it with an interrupt. So as a test case executes that basic block, it will trigger the interrupt, and thus we know that it has increased code coverage. So now we want to ensure that no future test cases with the same code coverage as that first test case will also hit that interrupt and mistakenly be marked as coverage increasing. We will reset that basic block and move on. So remove the interrupt so that no future executions going through that basic block will trigger the interrupt and no other test cases will be mistakenly marked as coverage increasing. So how this looks like on a macro scale, we want to only trace those few coverage increasing test cases and simply filter out the rest based on them not hitting any interrupts whatsoever. So given the target application, we would modify it statically and apply these interrupts before we even run it. And then the first test case that hits an interrupt, we would trace it, then find all of its basic blocks that it would hit in a normal execution using a separate binary, and then remove all the interrupts respectively in this interrupt binary, and then move on to the next test case. So what happens over time is that as you encounter more coverage increasing test cases, more interrupts are removed. So as these interrupts become removed, these two binaries start to mirror each other structurally for all intents and purposes. So what ends up happening is that as fewer test cases, as the likelihood of finding coverage increasing test cases drops, the overwhelming majority, we call this the common case, the non-coverage increasing test cases, will be run without anything interesting happening between enter and exit of this binary. No interrupts, no tracing, nothing. And they will be run at 0% overhead, native execution speed. So we're basically only tracing the few coverage increasing test cases and running the rest without any overhead whatsoever. So how this looks like as we incorporate it into coverage-guided fuzzing. So we insert this filter right after this test case generation process and before this coverage tracing step. So here, for every test case that you generate, you would execute it first on this application with these interrupts inserted. And for the overwhelming majority that simply do not trigger interrupts, we would just throw them away at that step without even having to trace them. And for the few that do, we would run them on this tracing binary, we would extract their coverage, and remove the interrupts accordingly. So again, over time, as you encounter more coverage increasing test cases, interrupts are removed, and the common case is run on a binary without any extra overhead. So native execution speed in the common case. In our implementation, which we call untracer, we use the static rewriting black box-based tracing approach Dynast for tracing these few coverage increasing test cases. So moving on to our evaluation, our first question was we want to strictly isolate the tracing overhead of coverage-guided tracing and compare it to these other kind of de facto approaches that fuzzing relies on for tracing test cases. So we looked at some of the most common approaches, Dynast and QEMU and AFL's assembly time. So there's a mix of black and white box-based tracing approaches, as well as our coverage-guided tracing framework on Tracer. And to isolate overhead, we use single-core virtual machines to eliminate any kind of operating system interference. We stripped AFL to just its tracing code, and we selected pretty diverse benchmarks to kind of have a varied model of real-world behavior. And we compared the tracer execution times across 5 days worth of test cases, one test case at a time. So 5 days worth of test cases per benchmark and 5 trials per each one of these days worth of test cases per benchmark. So these are our benchmarks, and as you can see, we wanted to very carefully select benchmarks that were of varying type, varying file format, but most importantly, varying code. So no benchmarks here are from the same package or library. So we wanted to very carefully have a good variety of benchmarks. And our first evaluation question here was, how does coverage-guided tracing compare to tracing every test case with a black box tracing approach? And we actually beat them by quite a bit. So in comparison to these approaches which trace using a slow tracer every single test case, the fact that we are only tracing these few coverage increasing test cases brings us down to about 0.3% of overhead. So okay, we were thinking that this is a pretty good reduction. How do we compare it to kind of the fast tracing approaches that white box tracing offers for fuzzing? And from there, we looked at AFL Clang, AFL's out-of-the-box assembly time-based tracing approach, and we discovered that we actually beat them by quite a bit, so about 36% reduction compared to one of the fastest-based tracing approaches right now. And the interesting thing is that although AFL Clang by itself has lower overhead than Dynast, which is what we relied on, the fact that we were using Dynast so sparingly gave us such a strict advantage over AFL Clang, which, although it was faster, traced every single test case. So this gives some credence as to how coverage-guided tracing has a direct impact on reducing overhead across fuzzing all these different test cases. So our next question was, okay, how does this reduction in overhead impact the overall fuzzer throughput? So our goal here was to measure the total number of test cases done in a pretty reasonable amount of time. So again, we looked for 24 hours across 8 benchmarks, 5 trials each. We used QSIM, which is a very advanced kind of hybrid fuzzer, similar to Driller. It basically combines concolic execution alongside these naive fuzzing approaches. And we discovered that the fact that coverage-guided tracing reduces tracing overhead so much because it only traces coverage increasing test cases gave it a decisive advantage in producing more test cases overall than QSIM using QEMU to trace every test case and QSIM using AFL's assembly time white box tracing for every single test case. So pretty big reduction in overhead results in a pretty big advantage in number of test cases able to be executed over time. So to conclude, why is coverage-guided tracing such a good complement to these other approaches? So we know that fuzzers spend a lot of their time finding coverage-increasing test cases by tracing every single one of them and comparing each of their coverage to some globally stored coverage over time. And that this amounts to about over 90% of their time on average across naive and intelligent fuzzers alike. Yet over 99.99% of these test cases, along with their code coverage, are completely discarded. We see this as being a huge waste of resources. So in other words, we can better allocate these resources elsewhere in the fuzzing process to help find bugs in different ways. And this is where coverage-guided tracing fits in by trying to restrict code coverage tracing to just those test cases guaranteed to increase code coverage, and we filter out the rest at native execution speed. And this results in a performance advantage. We reduce the overall overhead of fuzzing execution to about 0.3%. And as a result, we boost the overall test case throughput between 70 to 616%, so quite a big advantage there. And because we focus on strictly filtering out test cases, and just to show we use Dynast, which is a very slow tracing approach, the fact that we are tracing so infrequently means you can, in theory, use whatever tracer you want, whether it's Intel PT or LLVM-based instrumentation, and even bring this overhead down closer to 0% over time. And because we focus on strictly filtering out test cases, we maintain orthogonality with these other great approaches like Angora and Vuser, which aim to improve the test case generation process. So we work with them. And with that, I would like to welcome you to download, check out, clone, fork our code, integrate it into your fuzzers, and get the best throughput possible. So thank you so much.
And we have time for questions. Please state your name and affiliation.
Heng Yin from UC Riverside. So the idea use int3 to trace blocks is not new.
Okay.
So in 2012, I just checked, in 2012 there's a block, use this idea to trace the coverage. And in fact, in our DARPA CGC team, we use this idea for fuzzing. So when you propose this idea, have you checked that this has been done for years?
The only approaches we've seen that use any kind of debugger interrupts were strictly these kinds of software engineering approaches that use it for unit testing. We did not find any approach that used a strictly coverage-guided tracing approach to, use interrupts at every single basic block and reduce the set of test cases traced. But I'd be happy to talk offline more about.
Okay, another question. So you talked about the throughput increase. Mm-hmm. What did you compare to? For AFL, it has this forking mechanism, so it kind of skip the.
Yeah, so we measured, so for every test case, sorry, I forgot to include this in my elaboration about it. So we had this baseline execution overhead, which was just the fork server, no tracing component whatsoever.
Okay.
So everything was scaled relative to that.
Hey, hi, Lucas Drazel from UCSB, Santa Barbara. So my question is, I can see how this would improve performance in the case for where your coverage metric is basic block coverage. Now, for example, AFL has a coverage metric that is branch-based coverage. Mm-hmm. With you including not tracing every single input that doesn't hit a new basic block, don't you basically remove every coverage metric other than basic block coverage, reducing it to basic block coverage? So
the thing about coverage metrics is it's a trade-off. Fuzzing is all about trade-offs, right? So if you have a deeper coverage metric like AFL does edges and hit counts, you're actually going to be writing that data structure a lot more. Interestingly, HongFuzz, a competing fuzzer, does just basic block level coverage, although they can incorporate edges as well through static transformations, but they do so without hit counts, and that's also a very successful approach. The point is, it's not really clear what the best coverage metric is for finding crashes in a reasonable amount of time on a real-world program. So we have some work kind of exploring that right now.
No, I understand that. I just wanted to know if you had an evaluation of the actual coverage increases over time versus something that, like native AFL, that uses a different code.
We focus strictly on improving performance, but our code is available, so if you'd like to look at our integration with AFL and compare that to standard AFL, you're more than welcome to.
Hi, Paolo Montezel from Politecnico of Milano.
Hi.
I was just wondering whether you tried to see how using your approach impacts bug finding, because I just saw like performance scores, but I haven't seen like bugs.
So in our kind of micro evaluations, we saw that we were indeed finding bugs, but because we're not trying to compete with these approaches that focus on better input generation like Vuser and Angora and ProFuzzer and Nuez in this session, we're just trying to increase their throughput. So we're strictly focusing on making tracing as fast as possible, and we feel that we would better complement them. So I think a more fair approach would be to do one of these approaches combined with coverage guided tracing versus the approach kind of natively.
Yeah, I get it, but like for example, let's say that your approach is faster, but in the end you find less bugs because you remove stuff that might be interesting. Have you tried to look at that?
So because these fuzzers fundamentally rely on either block or edge coverage, and coverage-guided tracing fundamentally can support block or edge coverage, we don't think that there's theoretically any reason that we would find less bugs. But
okay, well, thanks.
Yeah.
We have time for one more question.
Yeah. Youngjin Zhang from Oregon State University. So my question is about like you have used like the debugger interrupt to like the check if this branch is visited or not.
Yeah.
But what I think is the more important thing for finding bug is like not just code coverage, like how many times we repeat some of the loops or some of the function executions or something. But from the explanation, what I'm seeing is like you are just caring about the visit or not about the like how many times about the executing of some of the loops or like a bigger program executions. In this regard, I think like it'll be very hard to find some of the bug because like a code coverage itself only tells like can we reach to certain points, not about the triggering the vulnerability. So could you share your like some of the insights about the thoughts about like that?
So again, there's no real evaluation that's been done to show whether hit counts or edges, or excuse me, edges or blocks, or edges with blocks or blocks with, edges with hit counts or blocks with hit counts is the best metric because it's a game of do I want to sacrifice performance for precision? AFL itself does this kind of coarse consideration of hit counts. They use these kind of like very large buckets. We have some work that's trying to definitively answer that question. But as far as addressing hit counts, so because coverage guide tracing operates at the block level, we have, incorporating hit counts via static transformations is something that we're kind of exploring right now. So, answer your question.
All right,
We can
let's
talk
thank the
offline.
speaker.